Hello everyone and welcome back to AP Precalc. This is lesson 2.1. Let's get right into it. Alright, so finish the sequences here. Pause the video if you haven't done the bell ringer because I am about to go over the answer. The first one is an example of an arithmetic sequence. The rule here is going to be adding 2, so 3, 5, 7, 9, 11, and then 13. The next rule here is going to be multiplied by 2. This is an example of a geometric sequence. So 3, 6, 12, 24, 48, and then 96. The third one here is an example of what we call a recursive sequence, which is an example of a Fibonacci where the previous terms impact the term after it. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34, and then 55 there. Now the next two are kind of fun. The first one is J, J, and A for the first day of every month. So January, February, March, April, May, June, July, August. So January, February, March, and so on. And then the next one is going to be E and T for 1, 2, 3, 4, and so on. And so 4, 5, 6, 7, 8, 9, and 10 there. All right, so what is a sequence? A sequence is a function from the whole numbers to the real numbers, meaning we can plug in any whole number, which is starting at 1 and then counting up with only integers. And then we will get any real number. So that would be a decimal place. You could get 2.5, you could get pi, whatever your real number is what you could get. And what this means is the whole numbers is going to be our inputs, so 1, 2, 3, and then our real numbers are going to be our outputs. So a good example of this is if we have the sequence, right, 3, 6, 9, and so on, our first term is going to be 3. So here our input is going to be 1, our first term is 3, our second term, which is 2, is going to map to 6, and then our third term, which is 3, will map to 9, and this is what it looks like graphically. And so the main thing here is this is very similar to a linear line like that, but we don't connect the dots. We leave them as discrete points, and we'll kind of talk about that later as well. So let's go back to our bell ringer here. Take that very first sequence, the 3, 5, 7, 9, and 11. Here, this is an example of an arithmetic sequence. And so this is because to get from one term to the other, we are adding the same number or subtracting the same number every time. In this case, this is plus 2, and this is going to be, plus 2 is what we call our common difference, which is commonly abbreviated as D. And so in this case, we could say D equals plus 2 or just regular 2 because it's going to increase by the same amount each time. Now, I know when a lot of people hear the word difference, they think of subtraction, but difference could be positive or negative in this case, depending on if you're adding or subtracting. But here, it's called common difference because this is the difference between 5 minus 3. So things to identify. If we just rewrite our sequence, our common difference is 2 plus 2, so we kind of already identified that. And then we have notation for each term. Our first term is going to be 3 in this case. We label this A of 1. So 1 is kind of like a position indicator where it tells us the position of the term in our sequence. 5 is our second term, so we're going to label that A of 2. 7 is A of 3. 9 is A of 4. 11 is A of 5. And so that is like position relative to the numbered term it is. So now let's take a look at our sequence here. So we have 3, 5, 7, 9, and 11. And then you have your n. So the first term is 3, the second term is 5, the third term is 7, and so on and so forth. And then to get from one term to the other, you're adding 2 each time. And so this is the equation you will want to memorize for your next quiz, test, AP exam, everything like that. But how do we get this equation and where does it come from? And so I want to show you this equation in terms of the sequence in particular with a specific example. And so what we're going to do here is let's relate the second term, which is 5, and show how can we go from 5 to 11, and how can this always be the case. And so we are going to start at 5. In this case, this is going to act as our a of k is going to be 5. In this case, is where we're starting at. So a of k is typically our starting term. And then we want to get to 11. We're going to set this as like our a of n in this case. And now what changes, or what do we need to do to 5 to move 5 to 11? And so here, if we look at it in terms of the sequence right here, we take 5 and we make a jump of plus 2, right? That's how big one jump is. That's the distance of one jump. So we are adding that jump of plus 2. This is our common difference here. So in this case, our common difference is 2. And then we're not just making that jump once, but we're making it 1, 2, 3 times. So this should be 3, our number of jumps. Now, if we don't write it out every time, how do we know how many jumps we're making between 5 and 11? Well, it's pretty easy. That's why these position indicators come into play, because you can take 5 minus 2 to get your number of jumps. So in this case here, you have 5 minus 2, and this is going to be our a of k, right? This is our a of n, so those are our two terms, plus your jump, which is d, your common difference, times the number of jumps, which is given to us by taking our position indicators, right, our n. And so you're taking 5, which is the position of the later term, so n, minus k, which is the position of the earlier term there, which is 2, because it was our second term was what 5 was. So hopefully that equation makes sense. If not, just memorize the equation verbatim, and then that should help you with the rest of this lesson. All right, so how would we graph this sequence? Here, let's take a look. So if we have our first term here, we're going to graph the sequence that we've been working with. So 3, 5, 7, 9, 11. I know it says 3 plus 2 in your notes. And so our first term here should be 3. Then our second term should be 5. Our third term should be 7. Our fourth term should be 9. And this is what it looks like graphically. Now the formulas and equations, this was the equation that we just went over, where d is going to be our common difference. Okay, a of k is going to be where we start at, our starting term. And then a of n is going to be our ending term. Where are we going to end up? So ending term. You could also put earlier term and later term. Whatever works best to help you memorize it is good with me. All right, so things to note. Arithmetic sequences kind of behave like linear functions. However, they are not continuous. So that's an example of an arithmetic sequence. That's an example of a linear function. Increasing arithmetic sequences increase the same each step, but the slope always stays the same. So in this case, our common difference, right, d, is very similar to, for a linear function, the slope m. And we will talk about more about the similarities and differences between those two in lesson 2 or point 2. All right, so for example 1, we want to find the first and seventh term of the sequence. This is pretty easy. When you're given a rule to find the first term, or a of 1, we want to just plug 1 in for n. So you should get 4 times 1 is 4, minus 3 is 1. So our first term is going to be 1 here. And then to find our seventh term, you're going to plug 7 in for n. This should be 28 minus 3, which should give you 25 as your answer there. For example 2, for each of the following, determine if the sequence could be arithmetic. If yes, identify the common difference. So here, S of n is just the same as A of n. S of n just represents sequence, so just another name to call it. To find it, I would recommend finding like at least the first 4 terms. So here, let's find S of 1, S of 2, S of 3, and S of 4. this should be 1 squared minus 3, which is negative 2. S of 2 should be 2 squared minus 3, which is 1. 3 squared minus 3, which is 6. 4 squared minus 3, which is 13. So you should get negative 2, 1, 6, and 13 as our sequence. And now that we have kind of like the first few terms of our sequence, right, we can see if it's arithmetic by looking at the jump from one term to the next. So this is plus 3, plus 5, plus 7. So because these are not the same, no, the sequence is not arithmetic. If we take a look at the next one, let's just find the first 4 terms again. So S1, S2, S3, S4. S1 is 6 minus 2 times 1. This is 4. S2 is 6 minus 4, which is 2. S3 is 0. And S4 is negative 2. So here, this would be the first few terms of our sequence. In this case, our common difference is going to be a negative number because we are subtracting. So here this is yes, and then our common difference is negative 2 there. All right. The third one here and the fourth one, these sequences are kind of already done for us, so it like saves us a step. For this one, we are just going to add 5 would be our pattern. And this applies to all of them. So here, this would be yes, and then your D would be plus 5. And then here, if we take a look, from 1 to negative 2, this is minus 3. From negative 2 to 3 is plus 5, minus 7, plus 9. So this is no, because you're not adding by the same number every time. All right, so the good thing about this lesson is that there's only really so many questions that I can ask you on a possible quiz or a test where I am not going to give you a whole lot of trick questions or wordy questions. But there's 2 main types of problems you will see, and I will walk through both of them with you today. And so the first one is walking through an example where we are given one term. So in this case, we're given our fourth term is 3, and we're given our common difference to be 2. We want to then find a general expression for a of n that can be used to find any term in the sequence, and then use that expression to find the 10th term in the sequence. So I would always start with writing out our equation. You're going to write this equation so much that you will have it committed to memory by the end of this lesson. So a of n equals a of k plus d, parentheses n minus k. And now what you want to do is clearly label everything in the equation. So let me write it out. So a of n equals a of k plus d times n minus k. There, where this is k, and then that's n. And so let's label our a of n, let's label our a of k, let's label our d, and then let's label our n and our k. So all 5 terms here. For this one, the first thing we would kind of want to do is when we're setting up a general equation for a of n, we want to basically set up an equation, kind of like in example 1, that you can plug any number into to get that nth term of the series or sequence. And so a of n will leave blank for now, and n will kind of leave blank for now. And then a of k is going to be our one term that we're given. So in this case, this was the 4th term. So this was a of 4, which actually had a value of 3. We were also given that our common difference is 2. And so what is important here is that you know that this is the biggest mistake I've seen students make, is that a of k is not the same thing as k. These two are very different. A of k is the term, which in this case is 3. However, k is going to be the positioning of that term, which if a of k equals a of 4, then k should be 4. Once we have this, we can plug in everything we know. So here, a of n equals a of k plus d times n minus k. This would be a of n equals 3, right, our 4th term, plus our common difference of 2, and then n minus the positioning of our 4th term, which is 4, right, because it's the 4th term. And that is our general equation, or general expression. And so here you can plug in 100 to get your 100th term for n. You could plug in a billion to get your billionth term. And so that's something that you can always do. Now we are looking specifically for a of 10 in this equation. And so all you have to do is just plug 10 in for n. So here a of 10 equals 3 plus 2, and then 10 minus 4. The biggest thing here is just make sure your order of operations is correct. So 6, 3, you're not going to do 3 plus 2 first. You're going to be doing the multiplication. So the 2 times 6, and then you should get 15 as your 10th term there. So make sure your order of operations is correct. If you did it the wrong way, you would get like 5 times 6, which would be 30, which is obviously not 15. So you would get the wrong answer if you mess up your PEMDAS. All right, so for example 3, pause the video now, try this one on your own because I will go over the answer. So here a of n, write out your expression. So a of n equals a of k plus d times n minus k. Here, we want to find a general expression for a of n, but we know we can set a of k equal to our one term that we were given. So in this case, a of k should be 8, and then from that, k should be equal to 3, the positioning of that number 8 in the sequence. We are also given our common difference as -3, so let's plug in what we know. A of n equals a of k, which is the number 8, minus 3, which is our common difference. So plus minus 3 is still just minus 3. And then here n, we'll leave n and a of n as is. And then minus k, which in this case, remember, k is 3. So make sure you do not put 8 here. You put 3, and make sure you put 8 here and not 3 for a of k. All right, this is our general expression, so that's the answer to part A. And now we want to find a of 12, so our 12th term in the sequence. So this is going to be equal to 8 minus 3 times 9, which is 8 minus 27, which is minus 19, should be our answer there. All right, the next walkthrough example that you could see is here we are not going to be given our common difference. That's something that we were given in the first type of problem. This time it's a little more fun, a little longer and harder, where we are going to be given 2 terms of a sequence, and then the first thing you want to do is find your common difference, and then basically start the rest of the problem that we kind of did at the beginning. So kind of just then once you have your common difference, you can treat it like a regular problem. Right, so first set up your equation. So a of n equals a of k plus d times n minus k. Once we have that, we want to plug in everything in the equation except for d, because that's what we want to solve for. So we want to find an a of n and an a of k to plug in. Remember, a of k is going to be your earlier term or starting term, and a of n is going to be your ending term or your later term. And so in this case, when we are given our second term and our 7th term, we're going to set a of k, which is our earlier or starting term, as our second term instead of our 7th term, which has a value of -2. We are also going to set a of n, which is our ending term, as our 7th term out of the 2, which has a value of 13. So then this would make k equal to 2 and n equal to 7, pulling those directly from the subscript. And now we can plug everything in, right? A of n is 13 equals a of k, which is -2, plus d, which you don't know yet, equals, or times parentheses, and then this is very important. It's not 13 minus -2, it's 7 minus +2, because it's n minus k, right? Here we can just solve this equation. So 13 equals -2 plus d times 5. Add 2 to both sides, and then divide both sides by 5 to get your common difference to be 3 here. All right, so now that we have our common difference, we can plug everything in to our general equation. And so remember, a of k and a of n we had as a of k was a of 2, which was -2, and then a of n was a of 7, which is 13. What we can kind of do is forget about a of n, right? Kind of clear our mind of a of n, but we can keep a of k. Once we have that, we want to plug it into the equation. So remember, we started with a of n equals a of k plus d times n minus k. Once you have that, we're going to plug this in for a of k, and now we know our d is positive 3. So a of n equals -2 plus 3 n minus k, which is 2. And that's our general equation. And then if we want to find the 10th term, all you got to do is plug 10 in here. So -2 plus 3 times 8. Do the multiplication first, and you should get 22 as your 10th term in the sequence there. So for example 4, let me walk you through here. So here, write out your equation. A of n equals a of k plus d times n minus k. Once we have this, we want to plug in an a of n and an a of k. A of k is going to be our earlier term. So in this case, this is going to be a of 3, which is 7. And then a of n is going to be our ending term, or our later term, which is going to be our 8th term, which is 27 here. So plugging in everything, you should get 27 equals 7 plus d, don't know that yet, and then times, and then n is 8 and k is 3. So 8 minus 3. This is 27 equals 7 plus d times 5. 20 equals 5 times d. D equals 4. So now we know our common difference. We can now plug that in to our general equation for a general expression. So here a of n equals a of k. We'll just reuse this value. So 7 plus our common difference of 4, n minus k, in which case is 3. And that is our general expression. And now we want to use this to find a of 24. This is going to be 7 plus 4 times 24 minus 3. 7 plus 4 times 21. 7 plus 84, which should be 91. So that should be our answer for example number 4. All right, example number 5, there'll be, you could see questions like this pop up on a quiz or a test. And so several terms of the arithmetic sequence a of n are shown above. Find a general expression for a of n and use the expression to find the 17th term, a of 17. So here, don't worry about this when it's 0. So do not worry about that. Sometimes they graph it, but it's not important. So here, what we can pull from this is our first term of the sequence, right, when n is 1, is 6. So a of 1 equals 6. Our second term is 4. So a of 2 equals 4. Our third term is 2. And our fourth term is 0. So if we write out our sequence, right, it looks a little something like this. And because these terms are consecutive, they're right next to each other, we can find our common difference rather easily, which should be -2. And so now what we can pull from the graph is you can pull not only any one, you can pick any one of those, but you can pull one term, which in this case, let's just keep it easy, right? The first term is 6. And you can also kind of find your common difference as well. Our common difference is -2. And now we're solving a problem like the very first walkthrough example that we had. So doing this to find a general expression for a of n, a of n equals a of k, which in this case we'll set as 6, plus d, so -2, times n minus k. And the positioning of the 6, of that number 6, is the first term. So that should be our general expression for a of n. And then to find a of 17, this would be 6 minus 2 times 17 minus 1, which is 6 minus 2 times 16, which is 6 minus 32, which is -26, and that should be our answer there. All right, for example 6, you will need to first find your common difference because we are given two terms. So let's do that now. So a of n equals a of k plus d times n minus k. Here, we're going to set a of k equal to our earlier term. So we have our second and our sixth. We're going to set it as our second term. And then a of n is going to be a of 6, our later term, which is 9. And now plug everything in. So 9 equals 7 plus d times, and then n is 6 and k is 2. So solving this now, subtract 2 from both sides, and then divide both sides by 4 to get 1/2 equals d. So that would be our common difference. Once we have that, then we want to find a general expression for a of n. So remember, a of n equals a of k plus d n minus k. And now we can set or keep this as our a of k. So a of n equals a of k, which is 7, plus our common difference of 1/2, and then n minus k, which is 2 in this case. So that is our example there. And now we want to find a of 24. And so this should be here. All you're going to do is plug 24 into the equation. So 7 plus 1/2 times 24 minus 2. This would be 7 plus 1/2 times 22. 7 plus 11, which is 18, should be our 24th term there. Example 7 here. Here we're given two terms again, and we want to find the 12th term. So let's set up our equation. So a of n equals a of k plus d n minus k. Here our a of k, we're going to set as our earlier term, so a of 3, which is 5. And then a of n is going to be a of 9, which is 14. So plugging it in here, 14 equals 5 plus d times n, which is 9, minus k, which is 3. Solving this, 14 equals 5 plus 6d. Subtract 5 from both sides, and then divide both sides by 6 to get 9 over 6 or 3 over 2. Right? This is 9 over 6, which is your common difference. And so you could have this. You could have 1.5 equals d. This would be one where you could need a calculator for, so just be aware of that. Once we have that, then we need to set up our general equation. So a of n equals a of k plus d times n minus k. Once we have this, our common difference is, I'm going to work with fractions here, so 3 over 2. So a of n equals, and then keep our a of k there, so 5 plus 3 over 2 times n minus 3 is our positioning there. And then to find the 12th term, just plug it in. So this is 5 plus 3 over 2 times 9. This would be 5 plus 27 over 2, which then this is 10 over 2 plus 27 over 2 is 37 over 2, which is 18.5. And so B should be the correct answer there. All right, so for day 2 here, let's get right into the bell ringer. Pause the video now if you haven't done this yet, because I'm about to go over the answer. Here, we are given two terms. We're given our third term of a sequence to be 24, and our sixth term to be 9. What is our value of the 12th term? And so what you want to do here is set up your equation. So a of n equals a of k plus d times n minus k. Here, we're going to set a of n as our later term, and then a of k as our earlier term. So remember, you can kind of go alphabetically, right? K comes before n, so then a of k should come before a of n. This then would be 9 equals 24 plus d times n, which is 6, minus k, which is 3, given from those position indicators there. We want to first find our common difference. 9 minus 24 is negative 15 equals d times 3. Once we have this, divide both sides by 3 to get -5 as your common difference. Once we have that, then we can plug in a general expression for a of n. So a of n equals a of k plus d times n minus k. We can reuse this as our a of k. So a of n equals 24 plus, or this should be, and then minus 5. N minus 3 is our general expression. We don't need that here, but we want to use this to find a of 12. So plug that in. This would be 24 minus 5 times 9, which is 24 minus 45, which should give us -21 there. And so that would be how you would do your bell ringer. So your answer should be -21. All right, so let's take a look at your very first bell ringer last class, and that second example, that second sequence. This is an example of a geometric sequence, and just for this lesson, make sure you have your calculator out. But here, it's going to be a geometric because you are going to multiply by the same number to get to one term to the next. So here, from 3 to 6, you're multiplying it by 2, 6 to 12 times 2 times 2 times 2 times 2, and so on. And so each term or terms next to each other have what we call a common ratio. That's going to be that multiplier, which is called a constant proportional change because the proportion between 6 and 3 is 2. The proportion between 12 and 6 is 2. And so each term is multiplied by the same number to generate the next term. So this is our sequence before. And so let's kind of see how can we relate g of 2 to g of 5 in this case, just like we did last class. So here, if we take a look, the first thing you see is here our rule is multiplied by 2. So let's start at our second term, and then let's see how this relates to our fifth term. So here, how can we go from 6 to 48? So here we take 6 and we make that jump of not adding 2, but multiplying it by 2. Now, how many times do we make that jump? Remember, when you're multiplying, you're going to take 2 and you're going to keep multiplying it by 2. And so here you do 6 times 2, and how many times do you do that jump? You do it 3 times. However, we don't write it all out. We just write 2, and then because there's 3 of them, we replace this with 2 cubed. Now, how do we get that it's 2 cubed? This is because cubed, or that number 3, will come from the position indicators, just like what we did before, where it's 5 minus 2 to get your number 3, which is how many jumps you have to make. But in this case, a jump is multiplying it by a number. So this is really g of k, our starting term, times our common ratio, which is r, to the power, or the number of jumps that it's going to make, is n minus k, kind of like in our arithmetic sequence, and then this should get us to g of n. So that is how that formula comes from, or where it comes from. Things to note, geometric sequences kind of behave like exponential functions, but they are not continuous. So that's like a geometric sequence, that's an exponential function, but they are very proportional, so they increase. The percentage increase will always stay the same, meaning you're going to always be multiplying it by 2, by 1/3, whatever the number is, that number that you're multiplying by will stay the same throughout the sequence or function. So let's graph this one here. This was 3, 6, 12, and so let's graph that sequence there. So the first term is 3, the second term is 6, the third term is 12, way up there. So as you can see, this gets bigger and bigger much faster than it normally would. And so that is something that's key about exponential functions. So just a reminder, a geometric sequence will have successive terms that have a common ratio. This means that each term is multiplied by the same number to get the next term. The general form for a geometric sequence is like that. And then for each of the following, determine if the sequence could be geometric. If yes, identify the common ratio. So here we want to find our first 4 terms, I would say, of the sequence. This should be 3 times 1 squared, which is 3. 3 times 2 squared, which is 3 times 4, which is 12. 3 times 3 squared, which is 3 times 9, which is 27. 3 times 4 squared, which is 3 times 16, which is 48. And so here this is times 4. However, this is not times 4, so we know this is not going to be geometric. Now let's find the first 4 terms of this sequence, so S1, S2, S3, S4. S1 is 4 times 2 to the power of 0. Anything to the power of 0 is 1, so this is just 4. This should be 4 times 2 to the first. 2 minus 1 is 1. 4 times 2 is 8. This is 4 times 2 squared, so 4 times 4 is 16. And then 4 times 2 cubed is 32. So here, this would be times 2, times 2, times 2. So yes, and then our common ratio would just be that number 2 there. That should be our answer for part B. Part C, if we take a look from 1 to 3, you're multiplying it by 3. 3 then times 3 is not 9, or is 9, but not 2. So if that was 9, then it could be geometric, but it's not, so this one's not. And then here, from 16 to negative 8, this is times negative 1/2. So you could have a negative common ratio. That's possible. Negative 8 times negative 1/2 is 4, positive 4. Positive 4 times negative 1/2 is negative 2. Negative 2 times negative 1/2 is 1. So this is true. And then your R here would be negative 1/2. So negative common ratios are totally fair game, where they kind of oscillate between, or switch between positive and negative numbers, because that's what you get when you multiply by negative numbers. All right, so for example 9, consider the sequence defined by g of n equals 4 to the power of 3 to the, or 4 times 3 to the power of n minus 1. Find the first and fourth term. So here our first term should be g of 1 equals 4 times 3 to the power of 1 minus 1. 3 to the 0. Anything to the 0th power is 1. So 4 times 1 is 4. And then g of 4 would be 4 times 3 to the power of 4 minus 1. This should be 4 here. So this should be 4 times 27, which is 108 there. So that's going to be our 2 answers there. All right, so for example 10 here, we have one term and our common ratio, and we want to find a general expression and then find the fourth term. So this is going to be very similar to the arithmetic sequences. So first set up our equation. G of n equals g of k times r to the power of n minus k. In this case, here we're going to set this as our g of k, and then this is our r. So this would be g of n equals g of k, which is the number 12, times r, our common ratio of 2, and then n should be just n minus k, which is the positioning here, which is 1. So that's our general expression, and then we want to use this to find g of 4. So this would be 12 times 2 cubed, which is 12 times 8, which should give us 96. So that should be our answer there. For 11, same thing. So try this one here, except now you have a negative number. So this is going to be g of n equals g of k times r to the power of n minus k. This is then g of n equals, this is going to be set to our g of k. This should be negative 3 times our ratio of 10 to the power of n minus 3. And then we want to find g to the 10th, or g10, which is our 10th term in the sequence once you have your general expression. So this is going to be negative 3 times 10 to the power of 10 minus 3, which is negative 3 times 10 to the 7th, which is negative 30 million. So that should be our answer there. All right, so for example 12, we're finding an expression for g of n, and then we need to use that expression to find g of 10. So from the graph, we can pull g of 1 should be equal to 4, g of 2 should be equal to 2, and then g of 3 should be 1. So from this, our first three terms are 4, 2, and 1. And so from this, we can also get our common ratio rather quickly to get our common ratio of positive 1/2. And so now it just becomes one of those problems where we are given a term, which we can use g of 1, our first term is 4, and then our common ratio, which is r equals 1/2. Writing out our equation, g of n equals g of k times r to the power of n minus k, we can plug g of 1, or 4, in for g of k, times r, which is 1/2, so 1/2 to the power of n minus k, which in this case is 1. And so this is our general equation. And then to find g of 10, what we want to do here is you want to take g of 10 equals 4 times 1/2 to the power of 10 minus 1. This should be 4 times 1/2 to the power of 9. And then this should be 4 to the power, or 4 times 1 over 512, which is 1 over 128. If you use the calculator, you should get 0.0078125 as a decimal approximation as well. All right, so for example 13, we are given g of 2 equals 24 and r equals 1/2. Find an expression for g of n. So writing out our formula as always, we can plug in g of 2, or 24, is g of k. Our r is 1/2 to the power of n minus, and then in this case it would be 2. This is our general formula, and then to find g of 5, we would plug that in. So 5 minus 2. This would be one that I would expect you to do without a calculator. So 1/2 cubed is 1 over 8, or 1 over 2 cubed, and then that times 24 should just be 3. Should be your answer for example 13. For example 14, we're given a graph of a geometric sequence and then want to find which could be the expression. So here our first term is 9, our second term is 6, and our third term is 4. And so from this, what is our common ratio? So remember, our common ratio is always going to be the second number over the first number. So this would be our common ratio, which can simplify into 2/3. So that is going to be our r. So just from that, we can eliminate d and a that have a common ratio of 3 over 2, which is not 2/3. Once we have that, using our 2 points, we know g of 1 equals 9 and g of 2 equals 6. And so we could write two possible equations. We could write g of n equals 9 times 2 over 3 to the power of n minus 1, or g of n equals 6 times 2 over 3 to the power of n minus 2. Only one of these will match the equation, and that should be B. So B should be the correct answer there. All right, so now for the examples, we're going to have problems where we are given two terms, and then we need to first do what we did with the arithmetic sequences and find the value of r. In the last day, we found the value of d, so here it's just going to be r, and then use that value of r to write the general form, so g of n equals that, and kind of take off from where we did at the previous few problems. Right, so for example 15, here we have our equation, so g of n equals g of k times r to the power of n minus k. We know g of n and g of k. We want to plug in stuff for that, and so here g of k is going to be our earlier term, so we have our third and our sixth term. So g of k should be our third term, g of 3, which is -2. G of n should be g of 6, which is 128. This should be then 128, we can plug in, equals -2 times r, which we don't know yet, to the power of n, which is 6, minus k, which is 3. This should be 128 equals -2 times r cubed. Divide both sides by -2. You should get -64 equals r cubed, and then -4 to be equal to r. So now that we have our common ratio, g of n equals, and then we can reuse the g of k here. So -2 times -4 to the power of n minus, and then k here was 3. And to find g of 11, this should be -2 times -4 to the power of 11 minus 3. -2 times -4 to the power of 8. And now remember, when you plug in a negative number to an exponent in your calculator, make sure you put parentheses around the negative number. Otherwise, it won't do it correctly. And so you need to have parentheses around the -4 before you take it to the power of 8. But then this should give you a value of -131,072. Should be example 15. Example 16 here, we're given two terms, so you will need a calculator for this one. So let's set up our equation. This is going to be our g of k and then our g of n. So 1.5 equals 48 times r to the power of 7 minus 2. 1.5 divided by 48 is 0.03125 equals r to the fifth. To take a number to the fifth root in your calculator, take 0.03125 and then raise it to the power of 1/5, or 0.2, which is that as a decimal. If you take any number to the power of, let's say, 1/7, that's the same thing as taking the seventh root of that number. You should then get r to be 1/2 there, so that should be our answer. And then we want to find g of n, and then use that to find g of 11. So g of n equals, we'll reuse the same g of k, 48 times 1/2 to the power of n minus 2, because that is a 2 there. That's g of n, and then to find g of 11, this should be 48 times 1/2 to the power of 11 minus 2, or 48 times 1/2 to the 9th, which should be 3/32, or you should get 0.09375 as your answer there. For example 17, the first four terms of a geometric sequence are shown above. What is the common ratio? So here we just want to see what number are we multiplying 8 by to get -4. So remember, your common ratio can always be found by taking your second term over your first term, which is -1/2, which is what we're multiplying it by. So that should be your answer, D. If you take a look and just make sure, that also holds true throughout the entire sequence. And finally, example number 18, let g of n be a geometric sequence where the fourth term is -5, the sixth term is -45. Which of the following could be the value of r? So here we have our fourth term, we have our fifth term, which we don't know, and then we have our sixth term, which we know is -45. And what could be the value of r? So let's test it out by plugging it first just into the equation. So this would be our g of k, this would be our g of n, or sorry, g of 6 should be our g of n, this should be our g of k. So -45 equals -5. Whoops, let me rewrite this. Here we go. -45 equals -5 times r to the power of 6 minus 4, which is just r squared. Divide both sides by -5. You should get 9 equals r squared. And then remember, when you take the square root of any positive number, you're going to get plus or minus 3 equals r. So r should be either positive or -3, so D would be correct. It also makes sense, right? If we take -5 and you multiply it by 3, you're going to get -5 times 3 is -15. -15 times 3 is -45. But also if we multiply it by -3, then you should get the same answer from your fourth to your sixth term. So -5 times -3 is +15, times -3 is -45. So both of these would work. So D would be the correct answer there. If you guys have any questions, please come see me in office hours, and I will see you guys later. Bye.